So in this current module, we're starting with electrolytes. I put up an example template of a chemistry profile just to make sure that we're pulling all this together. So for example, when we're looking at this example profile, electrolytes are going to be, obviously some of the tests that we're doing within a profile. And so we're remembering that these usually kind of go together in a way. So we're going to, let's come up here. So measured with ion selective electrodes. In the instrumentation part that's in the other class, we probably went over that. But I wanted to go over it at this point. I love this ARUP webpage. You can browse test A to Z. Like I just browsed and found electrolyte panel. And what's so nice about this website, whether your lab actually uses ARUP as their reference lab or not, this is just open to the public. There's no sign-in. You can see for test what their methodologies are, and you can see here ion selective electrode, which is what we're talking about from the notes. You can see specimens, what's acceptable, what's not, storage. So it's a really nice website that if there are tests that are involved in some of our notes that you're studying for or whatever, this is a good resource for you for this class, and then also for in the future as a worker, this is a good resource for you. So touching upon ion selective electrodes, I was going to show you also, this is the web page from Roche about the COBOS, which is one of the main chemistry analyzers. And the COBOS, here where it tells you type of modules, that it has two different modules. One is photometric and one is electrochemical, because I can't say that big 16-syllable word, so I'm just going to call it electrochemical. In the photometric section of it, it tells you includes ISE. So when we are talking about the fact that electrolytes are measured with ISE, remember that's a small unit within this larger instrument. So that large instrument, when you're looking at that large instrument in your lab, it's doing more than one methodology within that large instrument. All right, so here's a little, just a few minutes, a little refresher on ISE.
Ion selective electrodes are used in clinical chemistry to measure concentration of ions like sodium, potassium, chloride, and calcium in blood, serum, plasma, cerebrospinal fluid, and urine. Principle: an ion selective electrode, also known as a specific ion electrode, is a transducer or sensor that converts the activity of a specific ion dissolved in a solution into an electric potential. A pH-selective glass electrode is immersed into the solution whose ion concentration is to be measured. When the ion-selective electrode is immersed into the solution, a potential difference develops between the inner and outer layers of the membrane of the electrode, which is related to the ionic concentrations of the solution. The voltage is theoretically dependent on the logarithm of ionic activity, according to the Nernst equation. Parts of an electrolyte analyzer.
Okay, so you are not responsible for anything she just said on the video for your exam in here, but it was a good review of information since that instrumentation module is in the other class, because on your BOC, it is good to remember this concept here. It'll have the buffer solution, the glass electrode, the ion selective electrode. It can be the ones we talk about here. It can be sodium, potassium. The certain electrode will be specific for whichever electrolyte it's measuring. And it measures, as she says here, the potential difference, the electric difference, basically, between the inner and outer. So that's a good little summation of ISE. But as far as your tests specifically in here, it's gonna come from your notes. So measured with ISE, in the body, sodium and chloride are in the extracellular fluid. Potassium is in the intracellular. I didn't mention bicarb yet because I want to make sure that we're all on the same page with this. If you look over here at the example chemistry profile, see it says carbon dioxide. Some hospital labs may call this carbon dioxide. Some hospital labs may call this bicarb. In the lab on these chemistry analyzers, on something like the Cobas or whatever a lab has like that, quite often they're measuring bicarbonate, but it may be reported out as a carbon dioxide. So bicarbonate is in the extracellular fluid as well. Potassium being in intracellular literally means inside the red cells. So potassium, and this is not highlighted, but it should be, because it's in the RBCs, it is greatly affected by hemolysis. So if you have gotten to do any rotations in the chemistry department, you have probably had that to where you had to reject a specimen because it was hemolyzed and the potassium was going to be invalid on it. Okay, the major electrolytes that we are going to go over: sodium, potassium, chloride, and bicarb. Those are the main four. Obviously, it's, the highlighted parts you are responsible for in the exam. Sodium, major cation of the extracellular fluid, and I have up here as a refresher for y'all that it a little summation list here so that you could see which one is which without having to flip through each one. So the major cation of the extracellular fluid, it gets excreted in the urine when the plasma amount of sodium gets too high. So just like other analytes we've talked about, the kidneys will take that excess amount and flush it out into the urine. So plasma increased sodium is associated with diarrhea, excessive sweating, and diabetes insipidus. Notice these are all things that will affect the fluid balance of a person's body. And then decreased sodium is associated with diuretics and Addison's disease, because diuretics move fluid out of the body, that fluid that's containing the sodium for the most part. Potassium, the major cation in the intracellular fluid, so inside the RBCs, increased with renal failure, increased dietary intake. There have actually been case studies of people who had high potassiums because they ate, like 20 bananas every day or something crazy like that. Also associated with metabolic acidosis. I'm not going to go down that road yet because we're going to be talking about acid-base balance later in the same module. And then decreased potassium is associated with vomiting and diarrhea. Chloride, if you will notice, prolonged diarrhea, dehydration kind of goes along with some of this up here. Sodium and chloride usually go together. So what it's increased in and what it's decreased in, well, it's not exactly word for word, but it will somewhat correlate for the most part. And then one of the modules, either in this class or the other class, we did talk about cystic fibrosis. Remember, cystic fibrosis is the increased mucus accumulation in some of the fluids, including in the lungs, and improper bile creation in the GI tract. They will have an increased sodium and chloride, because again, those usually go together. And so the sweat test is that gold standard test for cystic fibrosis. And so the sweat chloride, if it's increased, that's why it's associated with that disease process. And then bicarb increased is associated with metabolic alkalosis and emphysema, decreased with metabolic acidosis, diabetic ketoacidosis, and aspirin toxicity. And again, we'll talk about these metabolic alkalosis and acidosis later in the module. So again, these are the main four. The other three electrolytes that we're going to cover in class, because these are considered to be the other main clinically significant ones, are phosphorus, calcium, and magnesium. They go together in a sense as well, that not only do these up here work in a balance with each other, but these also work in a balance with each other. So we'll go over each one, and then we'll talk about a little bit more about how they affect each other. So phosphorus is absorbed into the blood from one's diet. The levels of phosphorus in the bloodstream is regulated by the kidneys. The kidneys will decide when to excrete extra phosphorus, or when to reabsorb it. PTH, which is parathyroid hormone, So in the hormone section from the last module, parathyroid hormone will increase renal excretion of the phosphate, which is the molecular form of the element phosphorus, which will then lower the blood level because it's being excreted in the urine. And vitamin D causes intestinal absorption and kidney reabsorption, so it will increase. So you need to know this hormone and this vitamin, that the PTH will lower the blood level of phosphorus, whereas vitamin D will increase it. And that's part of that balancing act that our body's hemostasis system plays to keep everything, in check. Increased phosphorus associated with renal failure, decreased associated with diabetic ketoacidosis and asthma. Calcium, technically calcium in our bodies exists in 3 different forms, and those are listed there for you: free, bound to protein, and bound to anions. The biologically active form is the free form. So about half of the calcium within your body at any given time is considered to be in the biologically active form. Calcium levels are regulated by parathyroid hormones, so by PTH, just like up here, vitamin D, and calcitonin. A decrease in calcium will stimulate a release of PTH. If you go back to that hormone module, the last section we had gone over, this is probably, I'm not going to flip back over there because I don't have it ready and I don't have to go through all those files. But I think that's one of the pictures maybe that were in the end of those notes over there, part of that feedback mechanism. So when the calcium, it goes down in the bloodstream, then the body is stimulated to release this hormone. The PTH will cause the calcium reabsorption to increase so that the calcium levels will come back up. When the calcium levels come back up to a certain level, then that will turn off the stimulation of the PTH. So the body stops releasing the PTH. Vitamin D, which is usually obtained by diet or sunlight, will stimulate calcium absorption in the intestines. So therefore, calcium D will also raise blood calcium levels. Calcitonin, however, decreases blood calcium levels. So when the serum calcium increases to a certain amount, then the body will release calcitonin to then decrease that calcium level. It does so by inhibiting vitamin D and PTH. So vitamin D and PTH will both increase calcium levels. They're both stimulated by a decrease. Calcitonin will inhibit those two things. Calcium, increased amounts of it in the bloodstream are associated with an overactive parathyroid or adrenal insufficiency. Decreased would be, rather than overactive, it would be a hypoparathyroid, so an underactive parathyroid. Decreased levels of calcium are also associated with chronic kidney failure and vitamin D deficiency. There is a disease process referred to as tetany. We talk about tetany in microbiology because, Clostridium tetani, I believe, is associated with a tetanus issue. But remember that is more than one. It's kind of like hepatitis is to the liver. It's more than one actual condition that can be brought about by this. So tetany itself as a condition is the constriction of those muscles. It can be caused by that organism, but it also is brought about directly by a decreased free calcium in the body. Sources of error for calcium measurements include oxalate. Now, when we say oxalate, well, actually all 3 of these, we're talking about the additives in the lab tube. So if it's drawn in a tube that's got oxalate, which I think is that gray top tube, but don't quote me on that part. If it's drawn into a tube that has citrate as an additive, or if it's drawn into a tube that has EDTA anticoagulants, it is going to affect your calcium result. Another source of error is hemolysis icterus in lipemia. All right, and then our third clinically significant electrolyte from this list, magnesium. Just like calcium, the free form is the active form. It is regulated in the kidneys through reabsorption and excretion, same as the previous ones we just talked about. PTH increases reabsorption in the kidneys and absorption in the intestines, so PTH will increase magnesium levels. Increased magnesium is associated with excessive antacids. And over-the-counter antacids actually have a lot of magnesium in them. And there are some people who, if they have chronic indigestion, that they go through a lot of antacids per day, it can actually cause a high magnesium level. And also associated with kidney failure. Decreased magnesium, GI disorders, which makes sense if you think about it. If they have GI damage, they can't absorb the magnesium in their intestines that they usually would. Alcoholism, this is talking about a chronic alcoholism where the person usually becomes nutritionally deficient, and so it's a dietary deficiency from that. And then hypercalcemia, a low calcium, because it's part of a balancing act, will affect is seen with a lower magnesium. This is just a little additive that because these three work so much together, that I came across. I don't remember now in which textbook, and I didn't make note of it, but it was one of the textbooks. How calcium and magnesium work together. Calcium excites nerves, but magnesium calms them down. Calcium makes the muscles contract. Magnesium causes them to relax. Calcium is needed for clotting, but magnesium works toward having the blood flow freely. So it almost sounds like that they're counteractive, but they are, but they aren't. It's more that they're complementary. Calcium and magnesium, definitely everybody would need a balance between the two. Magnesium is responsible for the body's proper assimilation and use of calcium. So calcium and magnesium affect each other. Even though they don't do the same task, they do complementary tasks. If one consumes too much calcium without sufficient magnesium, the excess calcium is not utilized correctly. So they can't function as well doing their own job if the other one is not also there. Now, calcium and phosphorus, so number 1 and number 2, also have a relationship with each other. And that is in this diagram here. The parathyroid glands are involved because they release PTH. We're going to ignore that little message. PTH. PTH acts upon the kidneys and will raise calcium levels and lower phosphorus levels. It will act upon the bones and raise calcium and raise phosphorus. And then the kidneys will also release vitamin D to the GI tract, which will then raise calcium and raise phosphorus. So part of this is all that feedback mechanism where one plays a balancing act with the other. Okay, this is an awesome chart from CAP. I love doing some of my CEU stuff through the CAP organization because they have some really great information. I tried to pull out just the most relevant parts for to highlight for your exam, but I wanted to include the entire chart because it is such good information. So phlebotomy factors that affect electrolytes. If the blood is collected in a purple top tube, which has potassium EDTA in it, then it will cause a false elevation of potassium. If the blood is collected in a tube with sodium heparin, then it will cause a false elevation of sodium. Some of this seems kind of basic, but if we don't go over it, it may not click for you and you may not think about it. If the tube is hemolyzed, false elevation of potassium, we did already talk about that one. Delayed centrifugation of a blood specimen for more than 2 hours after collection. So if the tube sits there as whole blood, or even, and the little chart doesn't point this out, but even if the tube gets centrifuged, if it doesn't have one of those separators to keep the blood off of the plasma, then the RBCs, which are still alive, keep processing things. So that can cause a false elevation of potassium because potassium moves out of the intracellular fluid into the extracellular fluid. Refrigerating a blood specimen prior to centrifuging it, false elevation of potassium. Anaerobic condition not maintained, false decrease in the CO2. Basically because gas is always going to move in the direction of most to least. It's going to move into the area where there's not as much of it. So if the tube is opened and it's open to room air is going to move into the tube. Carbon dioxide is going to move out of the tube. Prolonged tourniquet use and excessive fist clenching, false elevation of potassium because, and this part's not highlighted, but it still makes sense as to the reason, because potassium is moving from the intracellular into the extracellular. Okay, and then the last little part for this video, the anion gap, which on most profiles will be found after those first main four electrolytes, it represents the concentration of unmeasured ions. There are other charged particles, other charged ions in the body that affect our hemostasis, other than these main four and other than these additional three that we talk about. So this represents the concentration of those unmeasured ones. There are two different calculations used, and they're listed here for you. There is not one that's better than the other, but for BOC, they could have you responsible for either one. So you would need to have both of these memorized. They're really similar to each other. It's just that one leaves out potassium. So the first one is, and you notice the positive and negatives go together. So it's your positive ion minus your negative ions. Or the other one that has potassium, it's still the two positive ions now. So you're just getting the difference between the positive ions and the negative ions. Because the first formula leaves out potassium, you have a slightly different reference range. Part of the reason that there's two calculations is depending on the quality of specimen, potassium can vary a lot. I believe this was the first formula for anion gap that was developed, and then this one was created to take potassium out of the game. But technically, they are both correct, so you would need to remember both of these. An increased anion gap, so an increased measurement of the unmeasured ions, is seen with uremia, lactic acidosis, ketoacidosis, ingestion of methanol, which is rubbing alcohol, and salicylate poisoning. Decreased low serum albumin and hypercalcemia. Okay, so that is the main points for the electrolytes portion. Acid-base balance, I'm going to start off with a separate recording on, because it's people think about it being this really heavy subject, but it's really not that bad. And I'm hoping that I can present it to you all in a way that you can see it and see that it's understandable.